G'day everybody, in this video we're going to be focusing on different applications of light. We're going to be looking at the spectra of light and how we can use that to execute on techniques known as spectroscopy. So let's get into it. So we're looking at dot point 7.1.4, 5 and 6. We're still looking at the nature of light and answering the question, what is light? And now that we know that light is an electromagnetic wave and have a little bit more of an understanding of what that actually means, we're going to start examining the spectra of light, the various wavelengths of light, and some applications where we can begin to take advantage of our knowledge of spectra. This technique is known as spectroscopy, and it can be broken down into many subparts, but we're going to be focusing on how we can use it to identify elements, particularly when we're looking at stars. And we can also gain some more information using the spectroscopy of stars, where even though we're nowhere near them, and no one's ever been close to them to observe, face to face, so to speak, we can actually use spectroscopy to estimate surface temperature, rotational and translational velocity, density, and chemical composition, in other words, identifying elements. So our key learning intentions today are to explore some basic principles of light spectra and spectroscopy, and therefore understand how we can use some of these techniques to learn about objects in space, particularly stars. So, our spectrum of light. Essentially, we can have light of various frequencies, just like we've learnt about in junior school and year 11. And if they have a different frequency, this is because they have different wavelengths, right? As the wavelengths get shorter, the frequency increases because more waves can pass a certain point every second. And this is based on the assumption that all light, all electromagnetic radiation has a constant speed. And that speed, as we learnt about last lesson, was 3.0 times 10 to the 8 meters per second. That is a rough estimate. It is slightly smaller, but that is a rounded value to two significant figures. And as you have again looked at previously, there are different categories of electromagnetic radiation depending on their wavelength. That gives the different types of light all sorts of properties and therefore different applications. Quick reminder too about how light can behave, because we're going to start talking about these concepts quite a lot, and having a broad idea of the behavior of light and its consequences is going to be really important throughout this topic. First off, light can be absorbed into a material, meaning that the energy of that light is being taken in by the material itself. The material can also emit light. It can release energy. Sometimes a light is able to transmit, which means it passes through, depending on the angle that it comes in, as well as the types of material that we're transitioning between. Transmission can also lead to refraction, in which light bends as it moves between or through different materials, and light can also reflect. Particularly though, we're going to be focusing on absorption and emission today, because absorption and emission helps us to understand spectroscopy. Essentially, the study of spectroscopy is meant to be all about measuring light energy that's being absorbed by matter or light energy that is being emitted by matter. There are many ways and reasons that matter can absorb and take in or emit energy. However, the more common one, especially if we're talking about energy that is in, roughly speaking, the visible part of our spectra, all has to do with the absorption of energy in electrons. Now, between different topics and subjects in science, we should have an appreciation already that electrons exist in different energy levels or orbitals. And if we give energy to an electron in an atom, and its energy increases because that energy has been absorbed, the electron is able to move from a lower energy orbital to a higher energy orbital. And when it is in a higher energy orbital than what it could be, we say that it is in an excited state. Similarly, that means that the material can emit energy by dropping from this excited state to a more lower energy and stable state. A lot of the time we will see this phenomena using an energy diagram like the ones here on the right, where we see the electron absorbing energy and going to an excited state where the electron now has more energy, or conversely, when we have a high energy electron lowering itself to a lower energy state and therefore releasing the energy, the difference in these energy levels here. So this then brings us to our spectroscope, where again we are attempting to measure the absorbed energy or the emitted energy from different substances. In most scenarios, analyzing electromagnetic radiation can be quite difficult because the radiation that might be coming at a detector is going to be a mix of different waves, all of different wavelengths, frequencies, and energies. By taking advantage of the concept of dispersion, we can split our light, our electromagnetic radiation, into its subsequent frequencies so that our detector can analyze each of the individual wavelengths one at a time. And there's a few different ways that we can do it. We could use something like a glass prism, and that will split up the light into its constituent parts. You can also use something called a diffraction grating, which is a piece of technology that we will be looking at in more depth in inquiry question 3. And sometimes these diffraction gratings essentially are a series of small slits that bend the light in different ways, but in a predictable way, and that's the important part. And sometimes a grating is actually like a waved surface, which is able to cause reflection in all sorts of different directions. In any case, we're able to split out the light into a spectrum. It doesn't have to be visible in the diagrams, it just makes it easy to visualize what's going on. But we have all of our different wavelengths here, our long wavelengths on this side and our short ones in the center. And then we would be able to use a detector to be able to analyze essentially the amount of light that's passing through for each of the different wavelengths. This allows us then to generate an emission and or an absorption spectra. And depending on what source of light we're looking at, is going to dictate what we see at the end, what we intend to see, and how we analyze it. Let's say I've got a source of white light and I was to look at a spectrum. It would look something like this because the white light is just a combination of all the different wavelengths. And so we would then see essentially a rainbow when it's all split out, and we'd be able to show that as we progress along our wavelength, the brightness of each different type of wave has a slightly different value. They can be nice to look at, but by themselves are not particularly useful. What is more useful is to analyze an emission spectrum or an absorption spectrum. So let's say that we are shining light into this cloud of gas. As the light passes, some of the electrons that make up the matter inside this cloud will absorb some of the light. What that's going to cause, as we've seen before, is the electron to take in that light and raise to an excited state. When that happens and the light then hits a detector, what we'll notice is that there are particular parts of the spectrum where that light has been absorbed. Therefore, we don't see it in the spectrum, or if we look at this graph, we get these characteristic dips that occur because absorbance has occurred. This energy has been, I guess, for lack of a better term, removed or taken in by the cloud of gas. Similarly, if the gas has taken in energy, the electrons that are sitting in this excited state will not do so indefinitely. They will at some point release that energy as they return back to their ground state. And fittingly, as you'll see in this emission spectrum, the light that is being emitted, and maybe we'd see that as a glowing of the gas, match up with the lines where absorption has occurred. We would also only detect brightness or light where the matching absorption lines are. We wouldn't see it for any of the other white light because essentially if we had a detector say here and the light's passing through this way, that white light's not going to magically bend and come this way unless we, essentially do that on purpose and redirect the light. And once we have either the emission and or the absorption spectra, there's lots of things that we can do with that information to learn about things, particularly in space, that we have absolutely no direct access to. For example, this is a hydrogen absorption and emission spectrum. If you have pure hydrogen and you shoot light energy into the cloud of hydrogen, you will essentially see this absorption spectra once a light has passed through. And if you were to put a detector elsewhere to see what light is being emitted by the excited hydrogen, these are the wavelengths that you would see. And again, they are supposed to and do match up. This is due to absorption and emission of energy as electrons are transitioning from one orbital to another. Particularly the ones that we can see in the visible spectrum are for electrons when they start in the second orbital and absorb a little bit more energy. And there we can see our black lines. And then conversely, if we had the electrons, say, dropping from N6 to N2, we would then see the bands in our emission spectrum. Hydrogen specifically is something that we are going to be able to quantify and calculate for in a little bit more depth in Module 8. But for the moment, the key thing that I want to emphasize here is that this spectrum for hydrogen is consistent for any hydrogen and is unique to any other substance or element. So if we look at the emission and absorption spectra, say for sodium, depending on the source that you see, you may see some other spectral lines here in the blue and the purple region, but the highest intensity ones are most definitely these two yellow lines. And potentially, if you have burnt different types of salts before in class, you would have seen essentially that sodium does produce quite an orangey yellow light that is very characteristic of sodium itself. When we conduct flame tests for other different elements, we may see other spectra for them as well, resulting in, when all those colors mix together, different colors that we perceive with our eyes. Another example here is copper, and it again has its own characteristic absorption and emission spectrum, and when these colors emit and release, depending on the different colors when they mix together, as well as their relative intensities, we get our overall color here, which we can see is quite a green to blue color. So what we have here is an absorption spectra of a star. Essentially, all we're doing is we're pointing a telescope out into the sky at a particular star, and we see what kind of light is coming from the star and to us. And what we notice are that there are these locations of high absorbance, particularly 1, 2, and 3. And this is the absorption lines that we would expect to see from hydrogen. What this is telling us is that for this star, as light is passing through the outer edges of the sun, there's lots of hydrogen that's getting in the way, blocking particular wavelengths of light. And then once it gets into space, that light just keeps traveling indefinitely. There's no matter to block or cause absorption at any different point in the spectra. And that's the light that ends up getting to us and our eyes. And so what this is telling us is that because of these lines in particular, the sun still has quite a lot of hydrogen in it, indicating that this is probably quite a young star. There are lots of different types of stars that exist at different parts of their life cycle and therefore have different compositions. And as we can see here, all of their spectra are slightly different, but can be classified and categorized into groups. This is a topic that we'll break down further in Module 8, but for the moment we are just introducing the concept of spectroscopy and how light is used in order for us to learn about the stars. So some other things that we can learn about the stars themselves are things like translational motion. How much is the star moving compared to us? And this is going to occur because there are going to be shifts in the spectra caused by the Doppler effect. If we have an object that's moving towards us, what we're going to see is a shortening or bluing of the waves. And if the object is receding or moving away from us, we would experience or see longer or reddening waves. What this means is these spectral lines that we see in the star are either what we call redshifted or blue shifted. And this redshift or blue shift depends on whether or not the star is moving away from us or coming towards us. So what we should notice here is that for these three sets of spectra, they're essentially the same fingerprint or barcode, right? The only difference is that these absorption lines exist at different parts of the spectra. And that again is the shifting that is occurring due to the Doppler effect. So assuming that we can identify some of these telltale lines and we know where these lines are supposed to be, we can account for that shift that occurs. And then using the Doppler equation, then account for the relative motion of the star compared to us. And get a little bit more of an idea of the translational motion of the star, where it is moving throughout space. We can also learn about the rotational motion of the star. While predominantly these Doppler shifts are going to occur because the star is either moving away from us or moving towards us, either or, there is going to be a very subtle Doppler shift due to the rotation of the star. If the star is rotating, then what we will see is that for parts of the light that is coming from the section of the star that's rotating away from the observer, we will see a red shift. And what that will mean is even though we do get a spectral line occurring, it will get a little bit broader because some of the light is going to have a slightly longer wavelength. And then on the other side of the star, some of the light is going to be ever so slightly blue shifted. And that blue shift is going to be because this part of the star is moving towards the Earth. Again, this is all relative velocity, so that doesn't mean that part of the star is moving away from the Earth and part of the star is moving towards the Earth, because if the whole star is moving away, then overall it's moving away, and if the whole star is moving towards, then the whole star is moving towards. But these are going to cause subtle differences in the relative velocity between the star and the Earth. And what that means is we're going to get absorbances that therefore occur at slightly different parts of the spectrum and make these absorption lines wider. And this is quite nicely exemplified in this little diagram over here on the right. We can also learn a little bit about the star's temperature by its spectra as well. There is a connection and a relationship between the frequency of light emitted from an object and its temperature. There is a mathematical model to describe this, and we can actually see the type of light which is being emitted from stars of various temperatures, but this is not a concept that we're going to unpack in detail until we get to inquiry question 3 as well. So I'm going to leave that until we get there. The last thing that we can interpret from the spectra of stars are their density. In those high density stars, what you're going to find is on the outer edges of the star, as the light's trying to pass through, there's going to be lots of collisions between atoms, leading to lots of different kinds of electrostatic interactions that is going to interfere with the light that's passing through and the types of light which are being absorbed by the matter of the star. What that means is you're still going to get spectral lines, but they are going to be broader, and particularly they kind of become a little bit fuzzy on the edges. And so the result here is quite similar to what we saw before with the rotational velocity of the star, but you should notice here that there is a distinct difference in the appearance of these broader lines. For a high density star in particular, they do again have that low resolution, fuzzy kind of look to them. So that takes us to the end of this video. In the next one, we're going to start looking at inquiry question 2, which is all about the wave model of light. And we're going to be talking about some different kinds of early models that were competing at that time. But until then, have a good one.